The volumetric compression ratio of an Otto cycle is 9:1. The compression index is 1.85. The expansion index is 1.32. At the start of compression, the gas is 69 kilopascal and 100 degrees Celsius. The temperature at the beginning of expansion is 1450 degrees Celsius. CP is, so I'm gonna need to modify the value. Yeah, that's right. So CP is 1 kilojoule per kilogram Kelvin, and CV 0.717 kilojoule per kilogram. R is 0.288 kilojoule per kilogram. So they want us to calculate the absolute temperatures and pressure at all the change points of the cycle. And in B, they want us to determine the heat. They want us to determine heat absorbed or rejected, excuse me. So you also need to state whether it is absorbed or rejected based on the calculation. So during the compression stroke in kilojoule, assume 1 kilogram of gas. So in C, they want us to determine the work done per kilogram of gas per cycle. And then D, the mean effective pressure in kilopascal. If the piston diameter is equal to the stroke, so the value of the stroke is 153 millimeter. So because we have an Otto cycle, so the starting point of the solution is to draw the PV diagram of an Otto cycle. So you have the pressure in kilopascal on the y-axis, and then we have the volume on the x-axis. So we have the state point, which marks the beginning of the compression process. So we go from 1 to 2, and then from 2 to 3 we have the combustion process. From 3 to 4 we have the expansion process, and then from 4 to 1 we have the exhaust phase. So now in question 1, they want us to determine the absolute temperature and pressure at all the changes point of the cycle. So at point 1 we have the pressure, which is 69 kilopascal, as well as the temperature. So you can say T1 is equal to 100 degrees Celsius, which is equal to 373 Kelvin, and then we have P1, which is equal to 69 kilopascal. So we are fine with that point, but we still need to determine, we only need to determine so we are fine with point 1. So they also give us the volumetric compression ratio. So we know that R is equal to 9 to 1, so that is not 1.1 here, it's 9 to 1. So therefore we can determine P2. So if we can determine P2 from this relation, because we know that P1 V1, so that is the polytropic relation between the volume and the between state 1 and state 2 when if we want to write the expression in terms of the pressure and the pressure and the volume. So we have N is equal PV and P1 V1 N is equal to P2 V2 to the power of N. So now we can say that to get the value of P2, we need to divide both sides by V2 to the power of N. So if we divide this side as well as this side, so now what's gonna happen is on this side we can simplify these two to remain with P2. So we're going to say P2 is equal to P1 V1 to the power of N divided by V2 to the power of N, which is also equal to P1 multiplied by V1 over V2 everything to the power of N. So now if you look at this relation here, the bracket, so that represents R, the volumetric ratio. So therefore we can conclude that P2 is equal to P1 multiplied by the volumetric ratio to the power of N. So we have the value of P1, which is 69, and then we have R, which is 9. So here we need to use N, the index value for the compression process. So we need to specify here. So NC, that C means compression. So we have NC, which is 1.32. So now if we work this out, so we get P2, which is equal to 1340 kilopascal. So that is P2. So now we have P1 and P2. So next we're gonna need to determine T2, because we need to determine in total we basically need to have 8 values, because we have 4 corners. So each corner needs the pressure and the temperature. So I'm going to have a new slide. So this is the next part. So we know that we have already P1, which is equal to 69 kilopascal. So we have T1, which is 373 Kelvin. So we also have P2, which is, so we have determined this in the previous slide, which is 1340 kilopascal. So having these three elements, and we know that the process is adiabatic, then we can determine T2. So we need to choose the relation that combine the pressure and the temperature. So if we say T2 over T1 is equal to P2 over P1 to the power of gamma. So here we need to write everything in terms of N. So I need to use N for compression minus 1 divided by index for compression. So from this relation we can find T2. So we can say T2 is equal to, so we just need to bring this to the other side and it's gonna multiply. So we have T1 multiplied by P2 over P1 to the power of NC minus 1 over NC. So then we can replace. So we have already determined T1 is already given. So we have 373 Kelvin. So we have P2, which is 1340 divided by P1, which is 69. So NC representing the compression index is 1.35. So 1.35 minus 1 gives 0.35. So we need to repeat it at the bottom. So we have 1.35 at the bottom. And if we work this out, we can determine T2. So the value of T2 is 805 Kelvin. So now we need to move, we need to determine the property of state 3. So I'm going to create a new slide once again. So we need to determine the property of state 3. So this is the between 2 and 3 we have isochoric process. For isochoric process, if we use the following relation here, So we say P2 V2 over T2 is equal to P3 V3 over T3. So since V2 is the same as V3, then the volume can cancel out. So we can determine the pressure at 3, because the temperature at 3 is already given. So we just need to bring, or we just need to cross multiply. So we can say P3 T2 is equal to T3 multiplied by P2. So from this relation we can determine P3. So P3 is T3 P2 over T2. So at this stage we just need to replace. So what is T3? T3 mark the beginning of the expansion process. So in that case T3 is 1450 degrees Celsius. So if we convert that into Kelvin, as I said, here it can be seen that the volume at point 1 is the same as the volume at point 4, and the volume V3 is the same as V2 is the same as V3. So we have this relation here, V1 is equal to V4 and V2 is equal to V3. We know that the volumetric ratio is given by V1 over V2, but since we know that V1 is the same as V4 and V2 is the same as V3, so this relation can also be written as V4 divided by V3. So the benefit to write this is to find the property of state 4, because we need to use, so if we say so if we use the relation of, so we have P3 V3 to the power of n expansion is equal to P4 V4 to the power of n expansion. So we can determine P4. So to determine P4, we need to divide both sides by V4 to the power of NE. So you also do the same thing here. So now we can simplify. So we can simplify these two to remain with P4. So you have P4, which is equal to, so just P4 is basically the relation which is on the left. So you have P3 V3 to the power of NE divided by V4 to the power of NE. So I can simplify this relation. So instead of repeating the exponent 2 times, I'm gonna repeat it twice. I'm gonna repeat it once. So we have P3 V3 over V4 to the power of NE. So now here we can see that V3 over V4 represents the compression ratio. It's also called volumetric ratio. So that the benefit of using this relation here. So we cannot use the relation combining the pressure and the temperature, or the relation combining the volume and the temperature. Well, we are going to get stuck easily. So the only relation that we can use is that one, because in this relation we can relation we can get the volumetric ratio, which is already, we can get the expression of the volumetric ratio, but since the volumetric ratio is given, we can just manipulate the formula and replace. So P4 is equal to, we have P3, which is so we have P3, which is 2414. So we need to replace it. So we have V3 over V4. V3 over V4 represents the volumetric ratio, which is the same as V1 over V2. Unfortunately, we are it is already given, so we just need to replace it as it is. So we have 9 to 1, which is the same as 9. So here we need to use the index, the expansion index, which is 1.32. So now if we work this out, we are going to determine the pressure at 4. Something wrong in this relation. Okay, let me just, so here we need to use V3 over V4 doesn't represent R, so R is equal to V4 over V3, not V3 over V4. So now here what we are going to do is so because we stated that R is equal to V4 over V3, but here we have V3 over V4, so we need to write this in terms of R. So if R is equal to V4 over V3, then V3 over V4 is equal to 1 over R. So I'm gonna demonstrate that on the new slide. Because we say that R is equal to V4 over V3. So if we cross multiply, so we're going to get R multiplied by V3 is equal to V4. So now here I need to determine this ratio in terms of R. To get this ratio, I'm going to need to divide this side by V4 as well as that one, as well as on this side. So if I do this, I can simplify. On this side I'm gonna get 1. So I'm gonna say, so here I have R multiplied by V3 over V4 is equal to, on this side I have 1. So here we have a multiplication. We need to determine the value of V3 over V4 in terms of R, because R multiply this bracket. When it moves to the other side, it will be divided. So I'm going to have V3 over V4, which is equal to 1 over R. So that is the expression I have. So instead of deriving all this relation, you just need to use the common sense. If V3, because here it is stated that R is equal to V4 over V3, then if I use the inverse, if V3 become on top and V4 at the bottom, then I will also change on this side. So if I inverse the left hand side, I must also inverse the right hand side. So this is basically what I have. So now I can say that P4 is equal to, if I use this relation, so it is P3. So here I need to use 1 over R, because R is V4 over V3 and not V3 over V4. So I need to say 1 over R here, and then I have the exponent. So if I work this out, I have P3 already, which is so P3 is 2414. So I have 2414 multiplied by 1 over R, which is equivalent to 9. So now on top I need to use the expansion index, which is equal to 1.82, and finally I get the value of P4, which is so if I calculate that, I'm gonna get, so I have 2414 multiplied by 1 over 9 to the power of 1.32. So I get 132.78 kilopascal. So that is T4, T4, P4, so the pressure at 4. So same thing, we can now determine the temperature at 4. So to determine the temperature, I'm gonna use the relation of the adiabatic process between 3 and 4 that combine the pressure and the temperature. So I'm gonna do it on the new slide. So the relation is, so we say T4 over T3 is equal to P4 over P3 to the power of n expansion minus 1 divided by n expansion. So we can determine T4. So we just need to bring T3 to the other side. So we have T4 is equal to T3 multiplied by P4 over P3 to the power of NE. So here we need to make sure that it is E, not C. Minus 1 divided by NE. So we have already T3. So we have already T3. So we have determined that from the slide. So T3 is 1450. No, 50 was not determined, it is given already. So we need to put it. And P4 is 132.78. Divided by P3. So we know what P3 is. So we know what P3 is. So P3 is 2414. So I need to replace that here. So I have 2414, which is our T3. So n minus 1 is 0.32, and then at the bottom I have 1.32. So if I replace that, I will end up with, so I'm gonna get the value of T4. So T4 is 718 Kelvin. So finally I have all the points on each corners, so pressure and the temperatures. So now the second question is, so they want me to determine the heat absorbed or rejected during the compression stroke. So we need to express that in kilojoule. So here they say assume 1 kilogram of gas. Okay, we need to do that on the new slide. So to determine the heat absorbed or rejected, always it's convenient to write the expression of first law of thermodynamic. So the first law states that Q is equal to the change in work done plus U. So U represents the internal energy. So that represents the work done. So that represents the heat. The heat generates, the heat added or rejected. It depends. So it depends on the nature of the process. So for this process, we know that the work done is given by, if we look in the formula sheet, you are going to realize that, so we are going to realize that the work done is given by, so only for adiabatic, only for the adiabatic or polytropic process. So the work done is given by P1 V1 minus P2 V2 to the power of NC minus 1, and then U, which represents the change in internal energy, which is given by M. So here we need to use CV multiplied by the change in temperature. So the final temperature, which is T2 minus the initial temperature, which is T1. So here they only specify for this process, the compression process. And remember that you memorize properly this law. So that is called first law of thermodynamic. So now we need to combine these two to get so to get the heat absorbed or rejected. So we're going to say Q is equal to, if we combine these two expressions, so we have P1 V1 minus P2 V2 divided by NC minus 1 plus M multiplied by CV T2 minus T1. So the next thing to do is to replace, we're going to replace P1 and V, so everything that are given here. So if we do so, we are going to have we can, because we don't have the volume, so we only have the pressure and the temperature. So this relation can also be written in terms of the pressure and the temperature. So if you write it in terms of the pressure and the temperature, so we're going to have M R T1. I mean, if we only write this in terms of the temperature instead of the pressure and the volume, so we're going to get MR T1 minus T2 divided by NC minus 1 plus, so we are going to repeat this as it is. So now you're gonna, sometimes you can be curious to know how I went from this relation to this one. It's very simple. Okay, I'm gonna explain you in the new slide. So we know that P1 V1 is equal to MR T1. So I need to explain how we can write the work down here. Instead of writing this in terms of the pressure and the volume, I can write this only in terms of the temperature. So I know this relation already. And then I can also say that P2 V2 is equal to MR T2. So now we need to replace this by that one and this one by that one. So if we do so, we're going to have the work done, which is equal to, instead of using P1 V1, I'm gonna use MR T1, because they are equal. P1 V1 is equal to MR T1. So I'm gonna replace it, this one by that one. So I have MR T1, and then I do the same thing for this part. So I have MR T2, and then I divide this by NC minus 1. So I realize that we have a common term, which is M and R, so they can go outside. So this can be simplified to MR. So I put it outside the bracket, and then I have T1 minus T2 divided by N divided by NC minus 1. So there we go. So we can also say that the work done is given by this relation here. So the reason to use this relation is because I don't have the volume. I didn't compute the volume. I only compute the pressure and the temperature on each corners. So now they don't want me to determine the work done. They want me to determine heat absorbed or rejected. But since I know that the heat absorbed is given by this relation, so we have the work done plus the internal energy. So this is called first law of thermodynamics. So I'm gonna go to the new slide. So Q is then given by, so from the previous slide I have already W, so I've expressed that in terms of the temperature. So you have mR T1 minus T2 divided by NC minus 1 plus mCV multiplied by T1 minus T2. So we just need to replace. So we have the mass, because here it is said that assume 1 kilogram of gas. So the mass is 1 kilogram. So I have R, which is 0.288, and then I have T1, which is 373, and T2, which is 805, divided by NC. So NC, which is equal to 1.35, so minus 1, and then I have the mass here is 1 kilogram. I have the value of CV, which is 0.717. I have the temperature T1. So T1 is 373, and then I have T2, which is 805. So if I work this out, I'm gonna determine, I will realize that so I'm gonna end up with Q. So that is Q for compression. It means it's between 1 and 2. So it's between state 1 and state 2. So I have Q from 1 to 2, which is equal to, so the answer here is 45 kilojoule, because it is negative. So that means we have, so that means heat is being rejected, not added. So when the compression takes place from 1 to 2, heat is rejected because we have a negative value. If it was positive, like from 3 to 4, if we calculate Q, we are going to realize that it is positive. So that means heat is being added. But in this case, heat is rejected. So now in question C, they want us to determine the work done per kilogram of gas per cycle. So here they want us to determine the work done of the entire cycle. So here there are two possibilities to determine the work done. So here I'm gonna show you all the alternative methods. So I'm gonna call that method 1. So here's the first method. We know that the work done is, in order to determine the work done in the process, we need to identify, in order to determine the work done of the entire cycle, we need to determine the process, the heat adding process and the heat rejection process. So we have the first process, which is from 2 to 3. So that is the heat adding process. So we have the heat rejection process, which is between 4 and 1. So here we have Q out. So now the work done is just the difference between the input and the output. So I'm going to say W is equal to Q in minus Q out. So now we need to find Q in and Q out. We can find that in terms of CV and temperatures of the process. So we have Q in, which is equal to M multiplied by CV. So we have T3 minus T2, and I will say minus Q out. Q out is also given by M multiplied by, so I use CV because the process are both processes are isochoric. So we need to start from, so we have T4 minus T1. So we have the temperature, we have the temperature at all the points. We also have the value of CV. So here the mass is 1 kilogram. So you just need to replace the value here, and then can compute. So here I'm gonna have 1 multiplied by CV. So CV is 0.717, and then I have T3 so I have T3 which is so I've already determined my T3 which is 1450. So I have T2 which is 805, and then I repeat again. So I have the mass which is 1, CV which is, and then I have T4 so T4 is 718 Kelvin, and T1 is 373. So if I work this out, I'll get the value of work done, which is 305 kilojoule. So here I don't need to say kilojoule per kilogram because it's already specified that the mass is 1 kilogram, so I don't need to repeat that again. So that's the first method. It's important to know all both methods because sometimes they can specify the method to use, but if you only know one, you get stuck. So here's the second method. We call it method 2. So to determine the work done of this cycle, we need to add the work done. So we need to add the work done of each process together. So in other words, we are going to say the work done is equal to, we have the first work done which is between 1 and 2. So we need to say W from 1 to 2 plus W from 2 to 3 plus W from 3 to 4 plus W from 4 to 1. Now see what's gonna happen here. We know that the process from 1 to 2 is polytropic. So we need to check the formula of the polytropic process to determine the work done. So the work done from 1 to 2 here is given by P1 V1 minus, but here we don't have the volume, so we need to write this in terms of the temperature only. So if we do so, we are going to have MR as we did in the previous slide. So we have T1 minus T2 divided by NC minus 1. So that is W from 1 to 2. So now this process is from 2 to 3, W is equal to 0, because the work done for the isochoric process is always 0. Why is it equal to 0? Because we know that W is given by, for a isochoric process, is given by P, the pressure, so we have the pressure multiplied by the change in volume. So we have V3 minus V2, but since V3 is the same as V2, so that means they can cancel out. So you get 0 here. 0 multiplied by the pressure, you still get 0. So that's the reason why the work done of the isochoric process is 0. Even if you check in the formula, you're going to realize that for this process the work done is 0. And then we have the process from 3 to 4. So the work done for this process is given by, so if we use the relation like this one, because all of them are polytropic, so we're going to have MR. So we start with the first point, which is T3, and the last point is T4, divided by, so here we need to use the end for expansion, minus 1. So this process is also isochoric. It means a constant volume. So for isochoric process, the work done is 0, because there is not so the piston doesn't move from 4 to 1, because the volume is the same. So that's why the work done is 0. If the piston is static, so there is no any work done. So now we are going to have MR T1 minus T2 divided by NC minus 1 plus, so here what we can do, just replace by the value, because we have already the value on each point. So we have so if you replace, you're going to realize that you're gonna get the same value, which is what we have determined in the previous 305 kilojoule. So we can use the first method or the second one, you get the same answer. So now we are going to create a new slide for question D. So now here there is something they want us to determine the mean effective pressure in kilopascal if the piston diameter is equal to the stroke. So what we are going to do here is, okay, we know that the work done of the cycle is represented by the area inside the cycle. So we have already determined this area, which is the work done. So because we have we say that work done is equal to area. So that area, so this represents the area of the cycle, which is the work done. So we have 305 kilojoule. So now we speak about mean pressure when we consider this area. We assume that if that area was rectangular, so what's gonna be the pressure? So it means we need to use a rectangular area having the same areas as what we have here. So we have the area of this shape, so that is not a rectangular shape. So we have this area which is rectangular, which is not rectangular. So A is equal to 305 kilojoule. So now if we assume that we have a rectangular shape, so that is a rectangle. It means on this process we can say that we have the pressure which is constant. So we say we have 1, so we have 1, 2, 3 and 4. So the mean pressure is basically the pressure at this, so the pressure from 3 to 4. So it's basically the pressure of that point, which is the same as the pressure of this point. So here we need to use this transformation. So we need to go from this shape to that one in order to determine the pressure. So now if both shapes have the same area, so I'm going to say that the area of that shape is also equal to 305 kilojoule. And we know how to determine the area of the rectangle. So the area of the rectangle is given by the longest side multiplied by the height. So the longest side represents the process. So the longest side represents the volume, because we remember that we are in a PV diagram. So on the x-axis represents the volume and the y-axis represents the pressure. So the mean, so we are going to realize that these two have the same length. So that I represents the mean effective pressure. So for a rectangle we know that area is equal to, so that is the pressure which represents the height multiplied by the volume, which is the distance in the x-axis. So in other words, the volume this distance represents the volume. So we just need to use this relation. So we are going to have T05, which is given by the mean pressure multiplied by the volume. So here we need to use the swept volume. So that represents the swept volume. So we need to have Vs here. So we can write Vs in terms of the diameter and the length. So we have the diameter that's gonna help us to determine the area. So the area is given by 0.53 square multiplied by pi divided by 4. And then we need to multiply the area by the stroke to get the length. But since they say that the diameter is the same as the stroke, so we have the stroke here of 0.153. And then we can make the mean pressure subject to formula. So I'm gonna create a new slide. So work done is equal to mean pressure multiplied by the swept volume. So the swept volume is symbolized by Vs. So now from this relation I can make Vs subject of formula. So I have Vs, which is equal to the work done divided by the mean pressure. So I have the value of the work done. So the work done represents the area, which is 305. So in fact I need to determine the mean pressure, not the swept volume, because I've already determined the swept volume from the values that are given already. So we need to say the mean pressure is equal to the work done divided by the swept volume. So we have the work done, which is equal to 305. And then we have the swept volume, which is given by the area multiplied by the stroke length. So we have pi multiplied by 0.153 square over 4, because that represents the area, and we have the stroke length, which is 0.153. So all this represents the swept volume. So just remember that to determine the mean pressure, I need to take the work done of the entire cycle divided by the swept volume, because the mean pressure is the pressure that can be found from the cycle, while assuming that the area under the area inside the cycle is rectangular. So if we work this out, we get the mean pressure, which is equal to so we get the value of mean pressure. So the mean pressure is 221 kilopascal. So that's the mean pressure here is basically the distance from, the height of the rectangle. So that is the mean pressure. So the mean pressure is seen on the x-axis, and from the y-axis, and the stroke volume is seen from the x-axis. So that represents the swept volume. So if we multiply the volume and the pressure, we get the area of the rectangle. So that area represents the work done, which was determined in the previous slide. So this transformation is useful to determine the mean pressure. So the mean pressure is the pressure which is assumed to be constant, because on this cycle the pressure changes from, so as we can see here, from 0.3 to 0.4 we have a change in pressure. But this one is useful because when it's come to determine the performance of the engine, we usually need to have we usually need to know the mean effective pressure, because we don't need to have the pressure at all the points. We only need to have one pressure from which other property can be determined. So that's it.